Hi, my name is Anisotropic. I'm presenting you DANI-Net, Uncalibrated Photometric Stereo by Differentiable Shadow Handling, Anisotropic Reflectance Modeling, and Neural Inverse Rendering. The objective of DANI-Net is to recover various surface properties from a collection of observed images which were taken by an orthographic linear camera with unknown direction lights and a fixed viewpoint. Through a neural inverse rendering pipeline, DANI-Net simultaneously recovers surface normals, spatial invariance diffuse reflectance, anisotropic specular reflectance, soft shadow maps, and light conditions. These recovered terms have many practical applications, such as relighting, which allows DANI-Net to generate realistic appearances under different lighting directions for both isotropic and anisotropic materials. Given the collections of observed images, previous state-of-the-art uncalibrated photometric stereo method integrates narrow fields and isotropic material model into the inverse rendering pipeline to recover surface properties under varying directional distance lights by minimizing the inverse rendering errors. However, this method has two limitations. First, it does not explicitly handle shadows but treat them as outliers. This is done by applying a pre-computed shadow generated from observed images within a threshold. Unfortunately, these shadow maps are sensitive to the pixel intensity, which can introduce noise. Moreover, the shadow maps cannot iteratively update to improve accuracy, and important cues conveyed by the shadow are not exploited. Second, this method employs isotropic materials models instead of an anisotropic one. This reflectance model may not be well suited for objects with anisotropic reflectance. DANI-Net aims to address these limitations by understanding and tackling two fundamental questions. The first question is about the significance of shadows and why they matter. Through our research, we are aware that the shadows convey crucial global shape-light cues that are instrumental in solving the uncalibrated photometric stereo problem. Hence, it becomes imperative to exploit these cues effectively. The second question is about the importance of an accurate reflectance model. This is answered by the fact that the inverse rendering loss acts as the driving force for parameter updates. Given its significance in the rendering equations, an accurate reflectance model plays an important role in deriving accurate surface normals. Based on these insights, we have proposed two crucial methods in DANI-Net. The first method is the differentiable shadow handling method. It aims to iteratively update the shadow map and efficiently exploit shadow cues for shape-light optimizations. However, implementing this method involves overcoming several technical challenges. In DANI-Net, the shadow should be directly calculated on the depth map rather than the normal map in a differentiable way. To achieve this, a depth MLP is employed to predict the depth value of a surface point, which describes the distance from the surface point to the camera. The cast shadow of the surface point is then calculated using this depth value, and the sigmoid function ensures differentiability. The method also addresses challenges related to computational cost by bilinear grid sampling. We additionally propose a surface normal fitting method that is necessary for inverse rendering. The proposed fitting method is efficient in backpropagations and preserves edges well. The second important method we propose is the anisotropic reflectance modeling method. Here, we represent spatial invariant specular reflectance as a weighted summation of anisotropic Gaussian basis instead of the isotropic Gaussian basis. This method integrates coordinate axis transformations and anisotropic Gaussian basis calculations to accurately model the anisotropic reflectance. Integrate all methods together. Eventually, DANI-Net forms up a inverse rendering framework that involves two MLPs. The depth MLP takes the coordinates as an input, passing through a positional encoders, and output the depth at that point. The predicted depth will be used to calculate the cast shadow and the surface normal. The material MLP takes the same input and output the diffuse reflectance and weights of anisotropic Gaussian bases. The specular lobe's roughness is a self-learned parameters, so as the light direction and intensities. The light conditions are initialized by a pre-trained CN model. All of the constant terms are regarded as inputs into the rendering equations to render the image's pixel values. The inverse rendering loss is calculated as the L1 loss between the rendered image's pixels and the observed image's pixels, and is back-propagated to the parameters and weights for iterative updates. The proposed two methods are two of the main contributions of DANI-Net, which is highlighted in the inverse rendering framework by the red square. To optimize DANI-Net, a three-stage training schema is applied. This schema involves iteratively dropping the total variation loss on the constant terms, and the silhouette loss is in different stages to avoid local minima. The effectiveness of DANI-Net is demonstrated through results on the diligent benchmark dataset. Comparing with other methods, the results show that the DANI-Net achieves lower mean angular errors for surface normal estimation, particularly in the cast shadow region. Additionally, results on Diligent 100 benchmark dataset highlight DANI-Net's ability to recover more accurate surface normals and render visually pleasant images under arbitrary light conditions for anisotropic objects made of coppers and steel. The ability of DANI-Net generates more accurate shadow than other methods is further validated by the qualitative comparisons on the shadow map. The importance of anisotropic reflectance modeling for DANI-Net to generate accurate normal map is validated by qualitative comparison on Diligent 100 dataset. As a conclusion, DANI-Net addresses uncalibrated photometric stereo in an unsupervised manner. Thanks to shadow handling and anisotropic reflectance modeling, DANI-Net can address more general objects with complicated shadows and materials. This paper also presents solutions for shadow calculations and surface normal fittings for differentiable shadow handling. Our unsupervised training manner and anisotropic reflex modeling are beneficial for generalizing DANI-Net to data from different sources. The reconstructed 3D surface materials can be used for many substring tasks such as relighting.